day, grade 11 chemistry students. Today what we're learning about again is solutions and solubility. Specifically, we are dealing with stoichiometry today. Stoichiometry, and we are going to use solutions and stoichiometry. So let's get started. Okay, so we're going to just get right into a question dealing with stoichiometry. And take a look at this one. 25 milliliters of 0.085 mole per liter aqueous sodium sulfide is added to 56.5 milliliters of 0.1 mole per liter mercury 2 nitrate. What mass of mercury 2 sulfide HGS precipitates? Well, first of all, we know this is stoichiometry because we're asked about information on mercury 2 sulfide. We're given information on sodium sulfide and mercury 2 nitrate, which are different chemicals. So if you have information on certain chemicals and we want to find information about a separate chemical, chances are you're going to be dealing with stoichiometry. And stoichiometry requires a balanced chemical equation. So we write down the chemical formula for our compounds. We write down the charges at the top. We write down the states. We cross over. So these are my reactants. So these are my reactants here, Na2S plus HeNO32. Then we're going to predict the products and recall the charges up here that I just eliminated. They will tell you what products you have. So Na is going to go with NO3 and Hg is going to go with S. Positive guys go first. We cross the charges of all our products now. And we realize that this NaNO3 is aqueous because anybody with a group 1 element or nitrate is going to be aqueous. Balance. Okay, it looks like it's balanced now. We write the information below our chemicals that relate to the chemicals. So this information here relates to sodium sulfide, so I'm going to write that below sodium sulfide. This information here relates to mercury 2 nitrate. Let's write that below there as well. It appears we want to find the mass of the precipitate here. So what we're going to do is we're going to, it's a limited reagent type question because we have two reactant amounts. One is in an excess, so we're going to have 2 molar hops that we're going to do. The one that produces the least amount of moles is going to be the correct answer. So we're going to do that. When we look at this though, this is a little bit different. This is very similar to normal stoichiometry, except now we have volume and concentration. That's the different part. So we can only do the molar hop if we have moles. So what we have to find first is our moles of each of these substances. Now recall that C equals N over V, so therefore N equals C times V. So N equals C times V, so therefore we are going to also remember that we need to change our units of volume to liters. So we're going to multiply each one of these by 1 liter over 1,000 milliliters. So again, notice I've taken my volume here, and that's the volume here. This volume here is the volume here. I've converted to liters by dividing by 1,000. We multiply it out, and we will get the moles of each one of our substances. Remember, this is going to be the moles for Na2S. This is going to be the mole for mercury 2 nitrate. So when we look at our moles here, we really remember that we can't tell who's limiting yet. Okay, we really need to see who produces less product to determine that. Now this is going to be my first molar hop, and this will be my second molar hop. Okay, so the first molar hop is from mercury nitrate to mercury sulfide, and it is a 1-to-1 ratio. So I'll show those 2 molar hops down below here. So the key to the molar hop or using stoichiometry is you have moles, and then you're going to change the type of moles you have. The type of moles we want to get rid of goes on the bottom. The type of moles I want to go to on the top. And if you take a look, the ratio is 1-to-1. So therefore, our number is not going to change. That means if you have this many moles of mercury nitrate, the same amount of moles will be produced. You can see my units cancel out, and that's the moles that we get. So you can see our second molar hop is very similar to our first. We're hopping from here to here. It's a 1-to-1 ratio. For every 1 Na2S, there is 1 HGS. So we have 2 answers for our mercury sulfide. Again, This is the limiting because it's the less amount. So Na2S was limiting because it produced less product. So therefore our moles will be 0.0021 moles. Now the question asks is what is the mass? So therefore, since we have moles, we're just going to use the molar mass of HCS, and that's going to allow us to find the mass that we need to find. So the molar mass of this compound per mole, 1 mercury and 1 sulfide, is 232.66 grams per mole. We obviously don't have that much. Remember that mass equals molar mass times moles. So our molar mass is 232.66 grams per mole times 0.0021. The answer we're going to get is 0.49 grams. So when we add these two chemicals together, what we will find is that we will produce 0.49 grams of our substance. This is the theoretical yield. This is how we do stoichiometry with concentration. Exact same way, except you convert to moles, same deal. The only difference in terms of stoichiometry and concentration or molarity is if we look at a problem like this, it asks us what is the concentration of chloride. So you have 26.5 grams of calcium chloride dissolved in 150 milliliters of solution. Well, if you look at this, you should realize that it's okay. I can just do a C equals N over V type problem, okay? My volume is going to be 0.15 liters, so we can rewrite this like this. The volume is going to be 0.15 liters because you are going to multiply that number by 1 liter over 1,000 milliliters. We don't know the moles, so we have to find it. So we keep in mind that our compound is calcium chloride. So remember there's two chlorides because the 2 plus comes down and then 1 negative comes down. We'd have to add up the molar mass. This is what we get. We know that moles equals mass divided by molar mass. So therefore, my mass is 26.5 grams. We're going to divide that by 110.91 grams per mole, and that will give us our moles. The answer is 0.24 moles. So therefore, my moles are 0.24 moles. Here we go. Just plug that in. Concentration. Divide those two, and we get a concentration. So we take our moles, we divide it by our volume. This is the concentration that we get. Now this is the concentration of calcium chloride. But what is the concentration of chloride? Well, calcium chloride looks like this in solution. And it's aqueous. And we know when it breaks apart, it turns into one calcium ion. And remember, this is ionic, so it doesn't break into diatomic chloride or chlorine. It breaks into 2 chloride ions. And this is significant because if our concentration is 0.150 moles per liter here, what's my concentration going to be at the chloride? Well, the answer is that it goes along with stoichiometry. Stoichiometry will follow stoichiometry will follow the coefficients. So if I have 0.15 moles here, I'm going to have 0.30 moles here. And the reason is because it's a 2-to-1 ratio. If you'd like to show that with stoichiometry, we can. 0.15 moles, okay, per liter. I guess you can put that in there. Calcium chloride. We want to get rid of calcium chloride. And we want to go to the chloride ion. And the ratio between the dissociation of these ions, or ionization of these ions, is 1 to 2. And that's why our number is going to be 0.3. So for class tomorrow, what I want you to do is we're going to take a look at a problem exactly like this. So this is your question. What is the concentration of the carbonate ion if 10 grams of lead-4 carbonate is dissolved in 100 milliliters? So go ahead and answer that question. This will be our problem of the day tomorrow, but I'd like to see you give it an attempt to see if you can figure it out. Start by figuring out what the formula is, and then go through the steps that I just did. Enjoy your day.
Oh, when the sunshine beckons to ya and your wings begin to unfold, I thought you bringing the songs you sing are gonna keep me